y'all. Good morning. Yesterday, we took a look at finding the determinants of a matrix. Today, we're going to take a look at finding the inverse of a matrix. So let's start with a number example. So we know that if I gave you a regular number and I asked you to find the reciprocal of it, you would just flip it. So this number right here is 7 over 1. So if you flip 7 over 1, that's 1 over 7. So that's called the reciprocal of the number 7. That is also called the multiplicative inverse of the number. We can have this same idea for a matrix. So matrix, we note a matrix with a capital letter, and our symbol for an inverse looks like this. So capital letters mean a matrix. That can be A, B, C, any letter that we want to. A capital letter is a matrix. And we find the inverse by putting this -1 symbol up here. If you think back to Math 3, we did the same thing. We were finding function inverses. We had this same symbol here. So an inverse of a number, we know this idea from way back when. And then the past couple of weeks, we've been studying matrices. So this is a matrix and this is the inverse. Also with numbers, if I do this 1 over 7, that's the same as 7 to the negative first power. Think back to properties of exponents. If I gave you something that was x to the third, and actually let's even do x to the negative third, and I asked you to rewrite that, it would be 1 over x to the third. So properties of exponent says I can flip it and have a negative exponent. With matrices, you do not divide. There's no such thing as dividing a matrix. We use this inverse symbol here. So since we cannot divide by a matrix due to properties of matrices and us not being able just to divide by the numbers like they are, we take the inverse instead of dividing. When you multiply a number by the reciprocal, you get the number 1. The same idea is true when we multiply by the inverse of a matrix. So if you take any numbers and multiply by the reciprocal, you're going to get the number 1. 7 times 1 over 7 is 1. 8 times 1 over 8 is 1, etc. and so on. 1 over 4 times 4 is 1. So today, as we work with this idea of the inverse of a matrix, if you take the reciprocal and you multiply, we're going to get the number 1. When you multiply a matrix by the inverse, which I'll show you how to do today, you get something called the identity matrix, which acts as the number 1. So this is our regular matrix. This is our inverse. If we multiply these two things, we get the I matrix, which is called the identity matrix. So it acts as the number 1. The same as I do up here, if I took two numbers and multiply by the multiplicative inverse, we get 1. If I take inverses for matrices, I get the identity matrix. If I go vice versa and take the inverse and multiply by the matrix, I get I. Sometimes there is no inverse at all. So as I go through and do calculations in just a few minutes, you'll see why some matrices do not have an inverse. So I have two examples down here that we're going to look at. This is our regular matrix A. This is just any matrix. I've already found the inverse for it. If we were to multiply these two matrices out, like we learned how to do last week, we would get a matrix that looks like this. This matrix is called the identity matrix. And I can go the opposite direction. I can take the inverse and multiply by the regular matrix and still get the identity matrix. So this identity matrix is like the number 1. So if you did 1/4 times 4 equals 1, this matrix times the inverse equals 1. But this is what an identity matrix looks like. So this is our original matrix, and this is the inverse, and it's equal to I. This is the inverse. This is our regular matrix, and this is I. So we cannot divide by matrices. Instead, we use something called the inverse of a matrix. Now let me show you how to actually find a matrix inverse. So this is our formula for finding the inverse of a matrix. So we find the inverse of the matrix by doing 1 over AD minus BC, and then you switch the letters over here. Now this right here should be familiar to you because that's what we did yesterday. This right here is the determinant. So yesterday we took the determinant, which was AD minus BC, and we're using the determinant today in our inverse formula. So our inverse formula says you do 1 over the determinant. You switch these two numbers. So wherever A and D are, you switch those two numbers. Notice it's now DA. And then we take the opposite of these two numbers. And that matrix, once we multiply it out, will give us the inverse of the matrix. And we only can find the inverse of a square matrix. Again, making some connections back to what we did yesterday. This is our determinant. And the determinant, you only can find the determinant of a square matrix. So 2 by 2, 3 by 3, 4 by 4, whatever the matrix has to be the same rows by columns. So let's use our formula and find the inverse for this matrix. So we have this matrix, 4, 5, 6, and 7. We're going to use this formula to help us find the inverse of the matrix. So here we go. If you need to label that this is A, B, C, and D, if you need to label that, there's nothing wrong with that. So nothing wrong with you labeling your variables so you can see where they go in your formula. So we're going to do 1 over the determinant. So this is 1 over. It says to do A times D. So that's 4 times 7. That's going to give me 28. So again, I follow the formula. It says to do A times D. 4 times 7 is 28. Minus, now it says to do B times C. 5 times 6 is 30. Now it says to switch the positions of your D and A. So switch the positions. So you flip-flop these. So 7 would go here and 4 goes here. So you just switch them. And then we take the opposite of these two numbers. So it was a positive 5. It's now negative. It was a positive 6. It's now negative. Now we go through and we simplify, and that'll give us our inverse. So this now is going to give me 28 minus 30 is negative 2. This stays the same. Now this is a scalar multiplication problem. So I take negative 1/2 and multiply all the numbers on the inside by negative 1/2. So our final answer would be negative 7/2. 2 negatives make a positive. This is 5/2. Negative 1/2 times negative 6 is going to give us 3. And negative 1/2 times 4 gives us negative 2. And this is our inverse. So if I were to take this matrix A, 4, 5, 6, 7, multiplied by this inverse, negative 7/2, 5/2, 3, and negative 2, if I were to go through and do matrix multiplication, I would get the identity matrix, which would be 1, 0, 1, 0. So again, the formula says to calculate your inverse, you do 1 over the determinant, you switch the A and D, and then you take the opposite signs of B and C. Let's try another one. So this is example 2. This time I have matrix 2, 3, negative 1, and 5. So the first thing we're going to do, the formula says to do 1 over the determinant. The determinant is AD minus BC. So 2 times 5 gives us 10. 3 times negative 1 gives us negative 3. Be careful with your signs here. This subtraction sign stays in the formula, and then 3 times negative 1 gave us a negative 3. Of course, when I clean that up, that'll be plus, but for right now, we want to go ahead and keep it separated. The formula also says to find your inverse, you switch A and D. So you switch these two numbers. So 5 goes here and 2 goes here. Then it says to take the opposite signs of these two. So this is going to be negative 3 and this is going to be positive 1. Now we go through and simplify. 10 minus negative 3 is going to give us 13. Bring this down. And now we multiply, and it's okay to get fractions. Nothing wrong with fractions. All of these are going to be fractions. So 5/13, negative 3/13, 1/13, and 2/13. So this is scalar multiplication. I took 1/13, which is my scalar, and I multiplied everything on the inside by that number. So this is our inverse. So if we were to take this matrix, which is what we started with, multiplied by this inverse matrix, we would get this identity matrix that I spoke of a little earlier. So anytime you multiply the original times the inverse, you get an identity matrix, which has ones along the diagonal. Let's take a look at one more problem. So this is example 3. And we're going to go through and find the inverse of this matrix. So it says we're going to start by doing 1 over the determinant. So the determinant is AD minus BC. So 3 times 8 is 24, and 6 times 4 is 24. Now we go through and we switch the A and D. So you switch A and D. So 8 is going to go here, and 3 is going to go here. Then it says to take the opposite sign of this number. So our formula is 1 over the determinant. You switch A and D and take the opposite signs of these. So this is positive 4. This is going to be negative 4. This is positive 6. It's going to be negative 6. We go through and simplify this. This is 1 over 0. Keep this number, keep this number, keep this number, and keep this number. Now, hopefully this is staring at you, and hopefully you think that this section is weird. It should be. We cannot divide by 0. That's impossible. So this matrix does not have an inverse. So we say the inverse does not exist. Inverse does not exist. So this is why every matrix possibly couldn't have an inverse to it. Some matrices have inverses and some matrices don't have inverses. If you get 0 in the denominator, you cannot divide by 0. So it makes the whole thing undefined, and the inverse does not exist.